Greetings, AP Calculus students. Mr. Ford here with a homework tutorial. We're looking at 631, and we mixed up some of the problems around in class a little bit because your work will look a little different than mine because my numbers are a little out of whack. We're doing, in your textbook, we're doing 85, 86, 88, 89, and 90. Excuse the hiccups. I got a little bad case of them right now. Now, in class, I believe we already looked at what my book says is 86, but your book will say is 85. We already looked at these three. I'll just kind of throw them up on the screen there for you to look at. Right there. Again, there's not much to say about these other than they can get a little hairy, but try just remembering that when you look at it in terms of chunks of the problem, it's actually quite simple. Question A is going to require both the product rule and the implicit differentiation. The product rule will separate out 13x to the third power as the first thing and y as the second thing. So here you have the original first times the derivative of y plus the original second times the derivative of 13x squared. And that's pretty much all you have to say about that. Question B does require you to know what the derivative of 2 to the x power is, which we do not require on the AP Calculus test anymore, but we have talked about it in this class. It's the natural log of the base times itself, like that. Exponential functions have kind of a self-replicating pattern to them, which we did observe. They are themselves times a constant, in this case, natural log of the base. So other than that, we're just using the tangent inverse function, the tangent inverse derivative that we learned today, which is 1 over 1 plus the input squared. And there you have it there and also there. Question C is nothing more than a chain rule problem with e to the x. Sometimes you can think about this as e to the u power, where u is equal to x squared minus 2x. And so the derivative is e to the u times u prime. Might be a way to think about this. So it's e to the original power times the derivative of that power, and that's where I got the answer from. Let's move on, though. We're going to look at 87 next, which I believe is your 86. We're going to use our calculator to evaluate each of the following definite integrals. So let's go crazy. Don't freeze, program. Okay, we're good. We're going to let our calculator do all the lifting here, but we're here to observe patterns. So let me slide over to the side here so we can look at. Well, the first one we know is 0. There's no real need to use the calculator for a because the integral from 1 to itself of anything is equal to 0. Next, we got the integral from 1 to 2 of 1 over x dx, which should give us 0.693. I don't know if you remember, but we have seen that number before. 0.693147. The next one, same exact problem, only we're going from 1 to 5. And that is 1.60944 or whatever. These decimals are going to seem inconsequential, but later on in the next question, it'll become apparent what's going on here. The integral from 1 to 1/2 of that thing, 1/2, is going to be a negative number. It's actually the same answer as part B, but it's negative, which we'll be able to explain in just a moment. And then we have the integral from 1 to e, which I know what the answer is without using a calculator is going to be 1. But maybe you're picking up on the pattern that I want you to see doing these problems. The integral from 1 to e of 1 over x dx, which should be 1. Yes. Now, again, I don't know how good your memory is or how apparent you remember what this pattern is, but question 688, which I believe is the same number now on your book and mine. What do you notice about the area under 1 of y equals 1 over x from 1 to any positive number as it relates to the natural logarithm? And here's what I want to check really quick. I'm just going to throw out some numbers here. The natural log of 2, the natural log of 5, the natural log of negative 2, and the natural log of e. And you can grab a calculator and crunch these numbers if you like to, but I'm just going to show you because I think you might already know what's going on. The natural log of 2 is 0.693147, and that is the answer that we had up here. The same thing is true. Actually, this is not negative 2, it's 1/2. There is no such thing as a natural log of a negative number. The 1/2 gives you the exact same answer, but it is the opposite. The natural log of 5 will give you the 1.60944. I promise, if you grab a calculator and try it, natural 5. You can see my calculator cam up there. It is 1.609. And the natural log of e we all kind of know to be 1. What we're building towards in this problem is the idea that the integral of 1 over x dx is equal to the natural log of x, which is the next derivative that we're going to talk about tomorrow also, because it is true that the derivative of the natural log of x is equal to 1 over x. Technically, this has got a plus c up, but yeah, there you go. Okay, anyway, I want you to see that ahead of time. Let's think about our exponential equations and their derivatives for problem 689. We're also going to set up for the idea of inverses. So let's go ahead and think about the graph of y equals 2 to the x and its inverse. So let's sketch really quick a graph of y equals 2 to the x. It starts at 0, and 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is going to be 4. And from there, it's going to be exponential and curve up forever. 2 to the 1/2 power is the square root of 2, which is something like this. And then you get the graph is going to start heading towards 0 but never touch it. So your graph is going to look something like this. There's your exponential curve. The only intercept of note is the point 0, 1. Now we are also asked, this is part A on this problem. Geez, these hiccups. We're also asked to graph its inverse. Now, if you don't know what the inverse of 2 to the x power is, I'll just tell you. It's the natural log of 2. Or, sorry, that's not true. It's the log base 2 of x that we're looking for there. Now, your modern calculator does contain a command that will allow it to graph pretty much anything you want. And when it comes to logarithms, I believe it's in the math menu, and I think it's down here somewhere. It's option number A, log base, which allows you to put the 2 in there and then graph the x. And if we go and look at the same graph that I'm looking at, the regular old normal graph, there is the exponential function, never touching 0, always going positive. And here is the logarithmic function, which never goes negative, never touches y either. It does pretty much the same thing, but it's reflected over the line y equals x. Inverse graphs have this property where they're reflected over the line y equals x, like this. So if you draw the perfect 45-degree diagonal line, y equals x, you can reflect your graph over that. Now this kind of makes sense, because in the world of logarithms, there's no such thing as a 0 answer or a negative answer. So you can't even ask the calculator what the log of 0 is. It doesn't exist. That would mean that the base to some power equals 0, which doesn't work. You do have an intercept at 1, 0, though. So this is kind of our introduction to the world of inverse functions. Let's take a look at B. We're going to write the equation for the... Oh, that's just the graph, so we haven't done it in the math yet. Question A is asking us to write the equation of the line tangent to y equals 2 to the x at its intercept. So here we go. For question A, that intercept is at the point 0, 1. So we're looking for an equation something like y minus 1 equals the slope, we'll say y prime, times x minus 0. All we got to do now is figure out what the derivative of that function is at 0. So for that, we're going to take a look at our original function, y equals 2 to the x power. We are going to take the derivative of that, dy dx, which is going to equal the natural log of 2 times 2 to the x power. Which, according to my calculator, natural log of 2 times 2 to the, and this is at when x is 0. So it's the natural log of 2. I don't need a calculator for this. Natural log of 2 times 2 to the 0 power. It's just the natural log of 2. Which I could put the decimal in there, but I'm going to use the natural log of 2 to keep it nice and clean. So the final answer is going to be y equals the natural log of 2 times x plus 1. Actually, I guess if I'm writing it clearly, it should be x natural log of 2, just so we don't get confused about what's inside of that logarithm. Just like that. That's for part B, or for part A. Part B is going to ask us to do the same thing. Write the equation of a line tangent to the graph of log base 2 of x at its x-intercept. Now, this is going to be interesting because we have no way of, we don't know what the derivative of the log base 2 of x is. We do know that it's happening at the point 1, 0. So we know that we are, so let me switch colors for this problem. We're at the point 1, 0. So I know at least it's going to be y minus 0 equals the slope, we'll say y prime, at x minus 1, or times x minus 1. Now we have no way of getting what that slope is. But if we take a minute to think about this like an inverse function, we do kind of know that if the slope is going to be the slope is just going to be kind of the reciprocal of what the slope is over the plot. That's how inverse functions work. So if the slope here at this point, if we draw our little tangent line on there, if that slope is the natural log of 2, whatever that slope is, let's say it's called y over x, because that's how we define slope. The slope at the inverse point, the reflection, is going to be x over y. It's going to be the same slope but flipped upside down. These two lines, by the way, should meet at the line y equals x if I'm doodling it correctly, but I'm kind of not. So our y prime in this case is going to be 1 over the natural log of 2 in this problem. I guess this is my long story short. We're going to take the slope from the other line and just take the reciprocal of it to find the inverse slope, is essentially how this works. This is setting up for how we will prove this in a later lesson. 1 over natural log of 2 times x minus 1. You can leave it like that for now. That's fine. Again, the slopes are just reciprocals of each other. Natural log of 2 and 1 over natural log of 2 in this problem. Question C is going to ask us to graph both of these tangent lines, and we're going to do that on the calculator. We've already got our two functions anyway, so let's go ahead and graph them and make sure we did it right. The first one was x times the natural log of 2 plus 1. And the second one was 1 over the natural log of 2 times x minus 1 in parentheses like that. Let's go ahead and add these to our graph and check to make sure we actually did it. There's the first one being a beautiful tangent line, and here comes the second one doing the same thing but kind of coming up at a different angle. It's going to take a little longer to calculate too. There it goes. Now it is worth mentioning, if you're paying attention, now that we got the graphs right there, the second part of this question asks what their relationship is. And here's the really cool part, is that they are inverses of each other. These guys will undo each other if you plug them in. If you take this entire expression here and plug it in for x up there, it will undo the rest of the function and leave you with x. The natural log of 2's will cancel out, and then the plus 1's will cancel out also, and you'll be left with just x. These are inverses of each other because they also reflect over y equals x. So these are inverses. That's the answer to part C. Question D says to use the tangent line in part A to approximate the value of y when 0.1. I don't want to do this because we're going to do it in the next problem. So let's not do D on that one. I'll update the Google Classroom assignment, so it's not that. Let's take a look at 690. We're going to do that in this problem anyway. So we're going to do very much the same kind of stuff in this problem. It's going to be a little bit of a different focus, though. We're going to start our adventure with the function negative 3 to the x power, which I'm going to go ahead and clear out all my other stuff and graph that. Negative 3 to the x power. Should be a different looking graph than before, because this one's actually going to go negative, because you're taking negative 3 and multiplying it by itself some number of times. That will always be negative, like that. Or, sorry, rather, I kind of got that wrong. You're taking 3. If you're looking at order of operations, let me make this a little more clearly. This is the opposite of 3 to the x power. I don't like the way it's currently written because it looks like it's negative 3 being raised to a power. It's the opposite of 3 to the x, which is why it's been reflected over the x-axis and everything is negative. We're going to write the equation of a tangent line at x equals 0. It's probably worth noting right now that we can tell from the graph that when x is 0, y is going to be negative 1. You could also get that by plugging 0 in for x in the equation. So we know that y is equal to negative 1. So we can start building our equation, maybe over here. We know it's going to be y plus 1 equals our slope, y prime, times x minus 0. Just using the point slope form, the reason why it's plus 1 is because it's actually y minus that value, negative 1. So I went ahead and changed that to plus 1 right now. The only missing piece, just like before, is what the derivative is, so we got to do that. We're looking for f prime. I'm going to do it down here. I'm looking for f prime of 0, essentially, in this problem. The derivative of negative 3 to the x is the negative natural log of 3 times 3 to the x power, like that. And if it's going to be f of 0, we'll plug 0 in for x. This is just going to be the negative natural log of 3 for our slope, f prime of 0. That's going to go in place over here. So Our final equation is y plus 1 equals the negative natural log of 3 times x. We'll go ahead and subtract that 1 over. So it'll be y equals negative x natural log 3 minus 1. And that should work pretty nicely. We'll go ahead and add that to our graph also, just to make sure we did it right. Negative x natural log 3 minus 1. Just going to push graph, and hopefully it does the whole tangent thing. Look at that. Perfect. Now, next question, they're going to ask us to estimate what the value of f of 0.1 is using our answer to part A. Now, this is kind of a different question. What they're not asking us to do is actually find out what f of 0.1 is. We actually can't do that without a calculator. I don't know what 3 to the 0.1 power is. I don't have a way of answering that without a calculator, but I can plug, well, kind of. You know what? This is not a good example. I still need a calculator. This is part B. But if I'm going to use my line, because here's the idea, is that if we zoom way in on this, for values of x that are very, very close to 0, the straight line is a pretty good guess as to what the curve is doing, because if you zoom in close enough on any curve, it's actually just a straight line for a very small window of time. So we're using the straight line to approximate what the curve is doing, which is a good estimate if we're right around here. It's not a great estimate if we're all the way out here or all the way down here, but right around 0, it's actually going to be okay. So our answer for 0.1 should be pretty close. So we're going to do negative 0.1 times the natural log of 3 minus 1. I don't like this example very much because you still need a calculator. Usually these examples are meant to demonstrate that you can estimate without using a calculator, but here we kind of need it. So negative 0.1 times the natural log of 3, which is that number, minus 1. So my approximation is negative 1.10986. Just for funsies, f of 0.1 would be negative 3 to the 0.1 power, and that is negative 3 to the 0.1 power. That is negative 1.1161. So you can see we're kind of close. We're only off by a penny. That approximation will get better and better the closer we get to x equals 0, where it is exactly correct. But there's that. The other question is question C, which is your approximation an underestimate or an overestimate of the actual value? And that conversation is all about the concavity of this graph. See how the blue graph is always concave down. What this means is that any tangent line that we use to approximate will always be above the graph for all values of x. So any value that we use the red line to approximate will be an overestimate, since it's always above the curve. If the graph was concave up, that would be the opposite. It would always be an underestimate. So it's all just about the concavity of this blue graph. Because this blue graph is concave down, this is going to be an overestimation. So to fully answer that question, I'll kind of write this sentence. Question C. Since f of x is always decreasing and concave down, any linear approximation, that is to say, anytime we use that line to approximate what the curve is doing, any linear approximation will be an overestimate. It's worth mentioning that you do actually need the decreasing part there, because if you think about it, let me draw some pictures with you for a moment. If you think about this, here is a curve that is decreasing and concave down, like our curve. Here's the curve that is increasing and concave down. I gotta think about it for a minute. Increasing concave down looks like this. So if you draw a tangent line pretty much any time on these two curves, actually I guess it is always an overestimate, isn't it? As long as the curve is concave down, you're going to have an overestimate with a tangent line. The line will always be above the curve. If you change the concavity, that agreement changes also. It becomes an underestimate. So it's all about concavity in that problem. That's a cool question. That's why I wanted to talk about it with you. Hey, thanks for watching this video. You guys are doing so great. There's a lot of stuff happening here. I think your September self would probably be proud of your February self for being this far into it. So there's a lot of stuff to take in here. Just keep up with it and allow yourself some rest time to make sense of the stuff that we talk about in class. Give yourself some time to make understanding happen, and it will all be great. I'll see you guys in the next video.